Turing 6502 PCB build. I'm Dr. Matt Regan. I want to give you a quick update where we are in the playlist. This is part 5, and this will be the last hardware video. After this, it'll all be about how we build a rulebook. Here's our Turing 6502 block diagram that we've developed previously in the playlist. This machine essentially consists of a rulebook, a notepad, and a way to keep track of the current rule and where you are on the notepad. The rulebook and the notepad for the PCB version are exactly the same as the breadboard version built in parts 1 and 2. And in part 3 we built the Arduino Nano interface, and I'm going to change that for the PCB build. The Arduino Nano, which you can see on the left, is great for breadboard builds, but it has a limited number of I/O pins. The Arduino Mega 2560 has a large number of pins, but it's most suited to Veroboard and PCB board builds. And with all those extra pins, I don't need the HC245 or the 257s anymore. I'll just connect these signals directly to the Mega. And because it's a PCB build, I had to do a schematic diagram. So here's how the schematic diagram is organised. In the upper left is the rulebook, upper right's the notepad, then down the bottom left we have the Mega, clock on the right, and display in the middle. This is the bare printed circuit board. And we can overlay the rulebook, the notepad, the Mega, the clock, and the display. I'm going to talk over the first part of this build, so unfortunately that's going to cut into the music. I'm feeling brave, so I'm going to use sockets for the EEPROMs, but I'm going to solder all the other chips directly onto the printed circuit board. I tend to solder the chips in first. I know other people recommend different orders, but hey, that's the order I like. Now here's a slightly unusual soldering technique I use, and I wouldn't recommend this if you're new to soldering. Usually we only do this for surface mounted parts, but it's a really quick way to solder through whole parts as well. Basically, I run a solder bead down the side of the pins and add in solder fast enough to keep the bead a reasonable size. It takes quite a bit of practice to get this right, so again it's not for beginners, and obviously you need to keep an eye out for solder bridges. The PCB bring-up is very similar to the breadboard bring-up, so I'm going to mainly highlight the differences. There are 7 ports on the Arduino Mega with a full 8 bits available. These are ports A, B, C, D, F, K and L. But port B is used for communicating with the SD card. So in reality there are just 6 full ports, which gives us a total of 48 pins, and another 24 pins scattered amongst the various remaining ports. I want to connect these 8-bit ports to our larger buses. This means I don't have to move bits around inside the Mega to reassemble what I'm looking for. Ports A, C and L are connected to the system memory. Port F and some of the bits in port H are used to drive the display and read the switches. Port K and the remainder of port B is used for reading the state. The clock's quite a lot more complex than the breadboard build. There's a clock high and a clock low signal, as well as a clock stop and a clock sense signal. I've done this because I want the Turing 6502 to run in real time, and I'm just not going to get there with the Arduino Mega clocking it alone. Now I'm writing the setup values for the data direction registers. I'll write it here, then move it to its final position later. I also want to set up the initial port values for those outputs. Now I'll just move it into place. And I'll put reset in the startup routine as well. Now I need to clock the circuit and snoop on the address bus and the data bus. This is actually easier than the breadboard build, because I don't have to worry about the 245s or the 257s. Again, I'll start off clocking it relatively slowly, and then I can just read the address bus and the data bus off the ports. Well, that didn't work. And yes, it does help if I lower the clock before I exit the loop. That looks better. So this initiation sequence after reset looks different to the normal 6502. For a start, the addresses appear to be occurring in pairs. Then I can see that the second piece of data ends up being the address on the next line. Then I have this other piece of data that doesn't make much sense at the moment, but we'll come back to that later. And these trends continue as we go on. Now we're getting to the good bit. Let's see if we can isolate out the pixel data, send it to the PC, and see how fast we can make it go. Isolate out the writes between 2000 and 3FFF. Yep, that looks right. We see the same burst pattern in the data that we've seen before. And now I'm going to go for broke. Set up the 20,000 count loop. Send the display update signal at the end of the loop. Check that a write's actually occurring. And finally, send the pixel data using the protocol we've been using. And there we go, Pac-Man. A little on the slow side still. Now I know from running the code there aren't that many writes, so I think I can take the overhead of a subroutine called per write. And I'll just move this pixel transfer into its own routine, and I'll just look at the upper byte of the address. This should save quite a bit of work per clock. Well, that's certainly better, but not great. I'll shorten the clock transition delays down to 2 Arduino cycles. Actually, that's 2 Arduino instructions. It's probably more like 4 cycles. Well, we're heading in the right direction. Now I'm going to pull out the big gun. Well, so to speak. I'm going to unroll this loop. So I'll clock it 10 times in the body of the loop, which should reduce the loop overhead by a factor of 10. And that's looking pretty good. Ultimately, I had to speed it up by a factor of 3.3 to get it to run in real time, but we're getting closer. Now I want to get my circuit running as fast as I can, so I'm going to look at the clock signal again. After the falling edge of clock, we read the symbol off the notepad and use this with the current rule to determine the behavior. The behavior is then latched into the flip-flops on the rising edge of clock. Then, when clock's high, we write the new symbol back into the same notepad location. Because we only have one memory access while the clock is high, we can make this portion of the clock shorter. So let's put some numbers on this to figure out how fast we can go. The fastest 628128 SRAMs have an access time of 55 nanoseconds, and the 27C322s have an access time of 100 nanoseconds. It takes the flip-flops 16 nanoseconds from clock to data out. Finally, the flip-flops need the input data to be stable for 12 nanoseconds before the clock edge. So this gives us an aggregate of 183 nanoseconds for clock low and 71 nanoseconds for clock high. Now in practice what I'll do is start with a faster clock and divide it down. And it seems to make most sense to have a ratio of 2 to 1 for clock low to clock high. Now let's say I divide the entire clock into 6 segments and have clock low for the first 4 segments and clock high for the last 2 segments. Then each segment should be 46 nanoseconds. And a clock period of 46 nanoseconds leads to a frequency of 21.74 MHz. Now it just so happens that 24.48 MHz is a very commonly available crystal that I just happen to have. But technically, I could also use a 10.738 MHz crystal and just have 2 to 1 ratios. If I want to add a video circuit later on though, it's much easier to generate the 7 MHz dot clock from the 21 MHz crystal. To help implement this, I'm going to introduce you to a new chip, which is the 74HC393, which is a dual 4-bit binary ripple counter. The truth table for this chip's on the right. CP is the clock input, and on the negative edge, it counts up by 1. When it gets to 15, it rolls back over to 0. Now instead of dividing by 16, I want to divide by 6. So I put an AND gate on Q1 and Q2, and feed the signal back into the master reset pin. Now, when it gets to 6, it instantly resets and 6 becomes 0. If I tap Q2 as my raw clock signal, it will be low for 4 clocks and high for 2 clocks, which should give me a low signal for 186 nanoseconds and a high signal for 93 nanoseconds, which is very close to what I'm after. I do have some 55 nanosecond SRAMs, but the ones I've soldered into this board are rated at 70 nanoseconds, so I'm going to be overclocking the circuit slightly, but let's see if it works. I want to be able to send back pixel data and C1000 commands, so I've integrated the Arduino into the system, but there's no guarantee how long it'll take the Arduino to respond. So for reads, I'm going to stop the clock if the main memory read occurs above C1000. Here's the schematic diagram from the PCB build. We can ignore the second counter for the moment, and I'm going to use this NAND gate to stop the clock on memory writes. And while the crystal-based clock is stopped, I want the Arduino to still be able to clock the overall circuit, and that's what clock high and clock low are for. And the last 2 signals are clock sense and clock stop. Clock sense means the circuit's been halted due to a read, and clock stop lets the Arduino take control of the whole clock circuit. And don't worry if the clock circuit looks a bit complex now, hopefully it'll become a bit clearer when I try to program it. And now for the build. Back to coding the Arduino. First I need to make clock stop an output and set it low. And now I'm going to leave the code the same. I'm just going to get rid of this unrolled loop and test to see if a write's occurring. This should have stopped the clock. So if I assert the clock stop signal, this should reset the clock counter and put it on the next read. Then if I release clock stop, it should just start running as normal. Now I need to manage the read. First I'm going to see if there's a clock sense signal, and if so I'm going to take control of the clock. When I manage the reads later I'll put some code in here, but for now I'm just going to raise the clock signal. Check if there's a write after the read, if so manage it. And then lower the clock signal and start it running again. I need to tell it that I'm using the Mega, not the Nano. And remove this extra close braces. Well, that looks right in some spots, but clearly it's not correct. I'll restrict it to writes between 2000 and 3FFF. And there we have it. This is displaying in real time. No speed up. And now we need to build the display. We have 3 rows of 4 7-segment displays, and we have some multicolour LEDs as well. Ultimately I want to use these to display the rule number, current symbol, the 6502 notepad, and the Apple II memory address that's currently in use. The displays are completely under the control of the Arduino, and each row has an octal flip-flop controlling it. And each column has a transistor to sync the current when it's on. There's our old friend, the 74HC138, to select which flip-flop to write to, and there's another octal flip-flop controlling the columns. Now only one column is displayed at a time, but we flick through them so fast it gives the impression of a solid display. If you look at the schematic more carefully, you'll see that the middle row actually has 2 74HC374s driving it. And this is basically because the blue LEDs aren't as bright as the red or green, so we want them on twice as long to make up for it. The display bring up was pretty straightforward, so I'm not going to go over in a lot of detail. But document the ports. Now this table stores all the 7-segment values for all the different ASCII characters. And here's our message. I use LED display to store our message. And I've just written a routine that we call regularly to update the display. First, we turn all the columns off. Then we write to the upper row. And before exiting, we need to turn on one of the columns and update the column counter. To write values, I need to make port F an output. And now set the middle left and middle right driver flip-flops. And finally, the value for the bottom row. And now we want to move our message into our display buffer and make it rotate. And there we have it. The display actually looks fine. I just had to put a Perspex shield over it to catch it on camera. And that marks the end of the hardware build for this playlist. Next video, I'll talk about reset and then the fetch, decode, execute cycle. So don't forget, like, subscribe, and sharing the video really helps.